Otherwise, I think we'll get started on session 2, which, so session 2 follows kind of the similar concept that we had in session 1, except we will cover less different topics and focus a bit more on 3 specific topics, and those are documentation, testing, and reproducibility. And we will start with documentation. Again, let's take a look first at the best practices that are already inside of the CIG best practices and what the Journal of Open Source Software recommends. And then we'll look at specific points and how to implement them. So CIG has best practices for documentation that say documentation for software should include instructions for installation, a description of the parameters that the user can set, explanation of the physics the code simulates, or more general speaking, explanation of the functionality of your code. Some examples for how to use it. A citable publication, that's what we're working towards here, towards a software publication, or a science publication works as well. And this documentation needs to be provided to the user somehow, online or offline. The improved level of standard best practice would then also include a description for a workflow for how to use this for a research project and a description for how to extend the code. And we will skip again a bit about the target best practices, which include additionally information on the limits within which the code has been tested, a wiki or a frequently asked questions page for the code, and documentation that is provided in a dynamic form, meaning dynamic content and a form that can easily change over time. The JOS best practices for documentation are a statement of need. What is your software designed for? Who do you want to reach? Example usage, functionality documentation, and community guidelines. I have skipped over the installation instructions and the automated tests because we have covered installation already in the previous session, and we will cover tests as a separate topic in this session. So let's take a closer look at the individual points and recommendations here. A statement of need. JOS requires authors to clearly state what problem the software is designed to solve and who the target audience of that software is. And CIG obviously also wants a explanation for what your software is made for. The important point here is that this is your elevator pitch for users who see your repository. Most users are looking for a solution to their problem, and maybe they Google for it or they have heard about your project, but they don't really want to spend a lot of time understanding what your project is. You want to have a 1 to 2 sentence, at most 1 paragraph description of what your software is, so that users can quickly evaluate, is this the software that I'm looking for? Let's take a look at an example again. Aspect states on its website and in its README, Aspect is a code to simulate convection in Earth's mantle and elsewhere. It has grown from a pure mantle convection code into a tool for many geodynamic applications, including applications for inner core convection, lithospheric scale deformation, two-phase flow, and numerical methods development. You don't necessarily have to follow exactly the same structure, but in general, following the structure of this code is this and that, and is intended to do X, Y, Z, is a very good format for such a statement of need, because it explains what your software is and what it's meant for. I would like to do a little experiment and see if we can come up with statement of needs for the software that you're working on. If you go to this website, or again, open menti.com and enter this code. Careful, this is a different code than the one that we used for the pre-workshop quiz. It's 3277-0881, or you can use your phone and scan this QR code. Then you'll get to a page, which I will likely have to advance so that you can. Actually, I think you're able to advance it on your own. And I would like you to try for a few minutes to come up with a statement about your software. Maybe you already have one. If you already have one, then think about, is it useful for users? Is that what your users are looking for if they want to understand what your software is? If you don't have one, try to write one in this style. Name of your software is something, and it is written in order to solve this problem. And we'll give it a few minutes and then take a look at the results. If this does not work for anyone, if you can't reach this website, let us know in the chat or unmute yourself and let us know. Awesome. Some very cool mission statements already. If you're still thinking about yours, feel free to work on it. If you've submitted yours and now you've seen another one where you think, oh, that's an interesting way to phrase this, feel free to include this way of writing a statement into your own. This is intended as an exercise to get you thinking about how to present your software, because that is what documentation is about. Documentation is your way of interacting with the user and telling them what your software is about. Ultimately, it's also your way to make sure that as few users as possible contact you with questions about your software. In the beginning, you might think it's great if you get more contact from users and questions about your software. But if you acquire more and more users, eventually you will notice that this will drain more and more of your time. And the documentation is your way of distributing the information without you having to spend time on distributing this information. One thing to keep in mind when developing your documentation is that users might reach this documentation in different ways. There are usually at least 2 different entry points for users into your documentation. They could either have downloaded your software and then encountered some problem while using it. A typical way for these people to find help is to look for a file that's called README or manual or something inside of the folder structure of your project. Another way users could have reached your project is through a website. If your project has a website, they could have Googled for projects, and this is one of the Google results, or you could have submitted a conference abstract or a publication and listed the website as the point of contact for your software, and so they will go to the website and see it there. So you need to have some information in both of these places, depending on where the user comes from. But you don't want to duplicate all of your documentation for your software. So eventually you would want to lead the user from both of these places to one definitive place where your documentation lives. And we will discuss different ways to do this during this part of the workshop. But let's first take a look at these 2 entry points, the readme.md and the website. readme.md is the most likely entry point, like I said, for people who already downloaded your projects, but also for people who find your project on GitHub. Because if you take a look at the starting point of your repository on GitHub, there is an explanation down here for your project, and this explanation is taken from a file called README in your repository. This could be a file that's just called README. It could also be a file called readme.md, like here, which has the benefit that it's a markdown file that allows you to do all of this fancy formatting, linking to images, and formatting that I've done here. Still, if you look at it, a markdown file in a simple text editor is just a text file that looks like this. The idea of Markdown is that you can read it like a text file, but that it allows you to include formatting instructions into the text file. We are going to talk about publishing your software in the Journal of Open Source Software or another software journal later. And as a matter of fact, you can fulfill many of the criteria that these journals have for your software already with a well-written README. So it's good to spend a bit of time writing a good README. Keep in mind that this is just one file or one page, though. So you want to keep it short enough to be readable in a minute or 2 or 3. You don't want to put all of your information into this one README file. It's not intended as the main place for your documentation. Let's take a quick look at what typical sections are that you would put into this README. So the software, this is now the software template that I have talked about before. And the sections in this README are, there's no standard for which sections to put there, but many projects follow the same scheme because it works. It has proven to work for other projects. So you want to start with some sort of heading that gives the name of your software. You want to include some links to a publication. If you already have published your software on Zenodo, or if you have a science publication that explains all of the details about the software, it's worth it to put it here at the top. You want to start with a section that's called About. And here you want to put the mission statement that we just wrote. This is what your users will see first when they open this page. Here's another example mission statement. You can include installation instructions here. Many projects have a file that's called install, which contains the installation instructions, but it's not necessary. If the instructions are short, you can also just put them into this section. You can also alternatively put them into your main documentation and then just link from this place to the place in the main documentation where you describe the installation. This has the advantage that when we will talk about the website, that you can also link from the website to exactly the same place. You don't want to keep one set of installation instructions here and another one on your website, because they will get out of sync. You can include a small section on how to run the software, maybe how to extend it. You most certainly want to include a section that includes instructions for how to cite it, because you would like users to cite your software, and many users don't know that they should cite your software, so you should make it clear to them and make it easy for them by including instructions here how to cite it. You likely also want to include a section that explains how to contribute to your software, or if you want users to contribute to your software at all. Maybe you don't want people to contribute to your software. It's finished. You don't really want to work on it anymore. Then you can also say here, this is a project that has reached its end of life. Feel free to use it or change it, but don't contact me with questions about it. You want to include information about how to contact you or how to get feedback or support about this software. And finally, maybe you have more places where they can ask questions, or you want to put in more information. You can put in a more information section. And typically you would end with a license section. This is maybe a bit unnecessary if you already include a file that's called license and that specifies the license for your project. But it's convenient to have this at the end, just to remind users that are not looking for the license file about the conditions under which they can use the software. We're going to talk about the contributing to our software part later in a bit more detail. Let's first take a look at the other entry point that people could take into your documentation, a website. So while you could use just the online repository on GitHub as the website and say your README is the main website, in this case, you have conveniently only one entry point that you need to keep up to date. This has some disadvantages because you cannot include fancy pictures, very large pictures. You cannot include videos or any interactive content. So most likely you eventually want to set up a project website. Maybe not if you just started and you are the only developer and maybe you just have a couple of users, but later on you probably want to set up a website. Typically there are three options how you could do that. You could traditionally self-host a website or have rent a server with some hosting service and have the website hosted there. Alternatively, you could host using your online repository. Both GitHub and GitLab provide services that are called pages, where you put the source code of a website into your repository, and GitHub then builds a website out of that source code and hosts it for you. I don't know if you've seen that before, but there are plenty of websites that are called something.github.io. These pages are built using GitHub pages. Alternatively, there is a project that has specialized itself on hosting online documentation for software projects. The project is called Read the Docs, and many projects use it to host their documentation. For now, I'll show you the documentation of the Relay project, which is one of CIG's software projects, this is one of the designs of such a documentation page. You likely have seen it before. In fact, we will take a look at the JOS websites later, and I'm pretty sure they are hosted by Read the Docs as well. The advantage of having using either the GitHub Pages service or the readthedocs.org website is that you can automatically build your documentation from the latest version of your software in your repository. So as soon as you change something, you will rebuild the documentation online. It's also relatively easy to link between the documentation and the source code because everything is online. You can also store multiple versions of your documentation. So for example, you can store one version for your latest release and one version for earlier development versions. Let me take a look. Yeah, here for the Rayleigh documentation, for example, there is a little selection box down here, and you can choose between the stable release and the latest development version. Theoretically, you can also set it up so that you can download it in different formats. So you can download it as a PDF file, or you can download it as an HTML package of HTML files. I mentioned before, when we talked about the README, that it's useful to include information on how to contribute to your project. And this has started a few years ago, well, more like 10 years by now, maybe. But GitHub provides the possibility to add a file called contributing.md in your repository that is specifically linked in certain places and directs people for how to contribute to your software project. Let me show you how that looks like. That was the link to the documentation about contributing.md. But if you go to an arbitrary GitHub repository, then contributing.md can look exactly like the readme.md. So it's the same markdown file format, and it's formatted to contain all of this information. And in certain places on the website on GitHub, there will be links to this file that say something like, want to know how to contribute to this project, click here, and then they will be directed to this file. Both CIG and JOS, well, CIG recommends to have such a file. JOS requires you to have such a file if you want to publish your software in JOS. Now, you might be confused or a bit uncertain about how that file needs to look like, but we have the same type of file in the software template, and they actually look relatively similar. The important part is that you include information on if you would like contributions from users, maybe a link to a tutorial about Git and GitHub and how you would like to receive the changes, and maybe some statement about how you will acknowledge the changes that users make in your project. It's helpful if you make clear to users that you want contributions and to make clear how you will officially give credit to the contributors of your software. Again, mostly in order to grow your software project to more developers and more users. Talking about the documentation, there are mostly two different main ways how people handle documentation in their software project. You could generate a PDF manual based on LaTeX files, one of the common ways to write documents in the geosciences or general in mathematical and physical sciences. Or you could aim for an online website, just like the one that I just showed you. Both of these approaches have pros and cons that you can weigh against each other. It will depend a bit on if you have already written documentation for your project, or what your community expects, or how much time you have available to set this up. We have templates for both inside of the software template. And we're going to talk a bit more about the online version later, because I assume that you know how you can use a LaTeX template to compile a PDF. Just briefly, some pros and cons of the LaTeX documentation. So like I already said, many people know how to write papers using LaTeX. And so using it for the documentation of your software is an easy step. It's great to render formulas and complex tables. Everyone is used to handling PDFs, so they are also easily archivable. You can upload them to Zenodo and create a DOI for them. You can send them as an email. They're easy to package and ship. Disadvantages of PDFs as documentations is that they mostly contain static content. They are statically generated. So you generate them once, and then you need to decide how often do you want to regenerate them. Also, they don't contain dynamic content. It's very hard to include videos inside of a PDF. You would have to ask yourself, how do I make this PDF available to all of my users? You would have to include it in some sort of website or some hosting service. One solution would be to include the PDF inside of your Git repository, but a PDF is a binary file, and Git is not very good at archiving and keeping track of binary files because they are so big and it can't store the changes. So every time you would update your PDF manual in your repository would grow substantially in size. And eventually your repository would be gigabytes of just history information of the different PDF versions of your documentation. It's also not very easy to link to individual sections of a PDF document that you have online. It's possible, it's not very easy. So say, for example, you get an email from a user that asks you about a problem, and you would like to reference section 3.5.2 in your documentation. Then the only thing you can say is check section 3.5.2 in the PDF manual. If you had an online documentation, you could send them a link and could say, check here. The online documentation has the advantage that, like I already said, it's always updated and it's always available. You can easily link to the repository or files. So you can include a link in your documentation that says, we have an example case that discusses this or that application, and make that a link that directly links to the files. It's possible to do that in PDFs, of course, as well. It feels more natural if you are already in a browser and then click on a link and get to that other page. I mentioned you can host multiple versions, you can host multiple formats, and it's very easy to search and navigate. So if we take another look at the Rayleigh documentation, there's a search box right here, and I can search for a phrase and it will list me all of the places where this is used. Again, this of course works in a PDF too. I can search in a PDF, but it feels more natural in a browser. The disadvantages of such an online documentation is you have yet another language that you need to write these source files in. We'll take a look at it later. It's just Markdown, so it's just text files with some special formatting, but it's yet another language to remember. You'll have to set it up one time, and we'll take a look at the configuration. It's not too complicated, but you have to work through it once. And you will have to decide where to host it, and then you're kind of bound to that hosting service. I mentioned both GitHub Pages and Read the Docs earlier. Both of them have been around for at least 7 or 8 years and are unlikely to discontinue over the next few years. Read the Docs is the de facto standard for many projects, and GitHub Pages is one of the standard websites to develop software. So they're likely going to be around, but it's a limitation. So are there any questions at this point? I see some messages in chat. Just wanted to check that. Yes, the question was, can read the docs work with Markdown files instead of restructured text files, which is the default? And the answer is yes. And we're going to take a look at that now. So the way, actually, before we do this, maybe let's define some terms that I'm going to use to explain this. There is a very convenient software that can convert Markdown or restructured text source files into an HTML documentation. The software is called Sphinx. There are some other softwares to build this type of online documentation, but Sphinx is the most widely used. These two formats are the formats you're writing in, Markdown or restructured text. Both work. Markdown is easier to learn, and since you may have written a readme.md Markdown file anyway, you're probably more familiar with Markdown. And Read the Docs is the website that then allows to automatically build this and host the generated documentation. So Sphinx is the software that does this conversion. Read the Docs is the website that actually hosts it. And it can be integrated into your GitHub repository. And we'll take a look at how that's done. Inside of the software template, there's a folder called doc for documentation and Sphinx template for the Sphinx template. This contains all of the information that's necessary to build an online documentation. The most important files are, let's start with the source code of the documentation. You will likely start, just like for a website, you will create a file that's called index.md. And this is just a Markdown file, just like the readme.md that we looked at earlier. If I show this like you would see it in a very simple text editor, it's just text. There are some special commands though. For example, if you want to include an image, you can create it with this structure, triple backticks, image, and then the path to the image. This image just lives in a folder that's called _static. There are sections, you can create lists, all kinds of other things. You can take a look through our template and see what kind of commands are available. But you can already see some of the features here. So you can highlight code, you can provide links, you can highlight code as boxes that are copyable, and so on. Maybe what I should highlight is there's a special directive for a table of contents. And in this table of contents, you can specify all other files that should be listed in your documentation. And if we take a look at how this looks like in the final rendered version, so this is just the build version of this documentation, then a table of contents can look like this. It will include links, not exactly to the files that we referenced, but to the sections, to the headings that are inside of those files. So it will actually look like a table of the content of a book and not a list of files. And this same table of content will also be used here in the left, in the table of content that's always visible in the sidebar. So this is what we just discussed was the content of the start page, but something else needs to tell Sphinx how to convert this. So for example, which design to use to set up this website. There are several designs available. This is done in a file that's called conf.py. So it's a Python file that has to be in the main directory of the Sphinx configuration. You don't need to write this yourself. You can, there's a small tool that sets up a basic Sphinx configuration, or you can just copy this file and adapt it to your changes. Most of this is pretty self-explanatory. So you need to specify a project name, a message that appears as a copyright authors. And then there are some extensions for Sphinx that you can specify. There are plenty of extensions for Sphinx. So in its most basic form, it creates simple websites. We included additional extensions to include Jupyter notebooks in that online documentation. So if you have Jupyter notebooks that live in your repository, you can automatically include them in the documentation. They will not be executable in the documentation, but you can see the output of the Jupyter notebooks. One of the other extensions that we used here is called MIST Parser, and this is the extension that allows to use Markdown instead of restructured text. This is in response to Sylvain's question. Yes. Likely the only other thing that you might want to change here are the HTML theme options. These are the options that specify how your website should look like and some additional configurations. So for example, you can specify if your table of contents should be collapsed with these little arrows here, or if it should be all visible immediately. You can specify which repository this is linked to. This allows you to have a link to the repository here, have a link to the repository here. Interestingly, so this is a special design of Sphinx. This is it's called the Sphinx book theme. And it allows you, for example, to suggest an edit or open an issue to your repository directly from this page. So if someone sees a typo in this file, they can suggest an edit, which will direct them immediately to the repository on GitHub. I have not tested this, and you can see this here. It's not working for this repository right now. I will have to investigate later why. For the Rayleigh repository, it works. Let's see if at least the open issue button works at the moment. So I'll have to look into why this, for the software template, the suggest edit button doesn't work, but the open an issue button works at the moment.
I think I got the path wrong.
Yeah, we will investigate later, but it's usually not too hard to figure out. Yes, this here, right, Lorraine? This likely needs to point to docs and yeah, okay. Anyway, so just to give you a feel for how this configuration file looks like. Again, you don't need to change a lot here, and a lot is self-explanatory. This is the place where you want to change things if you want your website to look different. The next file we should take a look at is the environment.yaml file. In order to be able to build this documentation online on Read the Docs, when you've changed something, they need to know which packages need to be installed inside of their virtual machine to build your documentation. For example, in our case, we used the Sphinx book theme that I mentioned. So we have to make sure that the Python package that contains the Sphinx book theme is installed on their system. And this is most easily done by including a file that's called environment.yaml. If you know about Conda and Python environments, you might be familiar with this already. But an environment.yaml file just specifies which Python packages to install for a certain environment. In our case, these are just very few. And you likely don't have to change anything here unless you want to use a different Sphinx theme, which is not pre-installed, or you want to use some fancy features which require additional Python packages. And the last file that we need to talk about is a file that does not live in the directory of the documentation, but in the main directory of your project. It's called .readthedocs.yaml, and it just tells read the docs how to build the documentation. In particular, by telling it where the conf.py file is inside of your repository and where the environment file is that we just talked about. Here you can also specify which formats the documentation to build in this case, PDF and HTML, but you can actually build this in more formats, for example, EPUB, if you want to make it available on ebook readers for whichever reason. And that's it. This is the setting to how to set up the source code of your documentation, how to make sure that Sphinx knows how to convert the source code into HTML, how to tell read the docs, how to build the documentation on the website. And then the last step is, of course, to let read the docs know that it should build this project. And for that, you would have to go to read the docs, create an account for yourself. You can link that account to your GitHub account. When you set up your account for the first time, it will ask you to link your account to GitHub. And then when you go to this website, readthedocs.org, you will have the option to import projects. These are projects that I have access to, and I could enable any of them to be built on Read the Docs. For most of them, of course, it wouldn't work because I haven't included the configuration. But here is the software template that we just looked at. And if we take a look at builds, you will see that by default, this documentation will be built every time the GitHub repository is updated. The way this works is if you import a project into Read the Docs, it will install a webhook between the GitHub repository and its own repository. Every time you change something in the GitHub repository, that hook is triggered and Read the Docs will rebuild your documentation for the latest version. And that's all the steps. If you follow the same steps, you will have an online documentation on Read the Docs. Any questions about this process? Okay, then let's move on. We're running a bit behind in time. I had planned to ask all of you if you prefer PDF. We do have a question. Do you need to set up a trigger action on GitHub or Bitbucket? No, you do not. When you link your account between Read the Docs and GitHub, and then you import the project on Read the Docs automatically installs a trigger on GitHub. On Bitbucket, I think you may have to install a trigger yourself. That's correct. I have not tried to combine Read the Docs with Bitbucket before. I'm pretty sure you can. You just have to set up the correct webhook, but you probably have to do it manually. If you have a minute or you still have the Menti question open, feel free to advance the slide by one and let us know which documentation you prefer personally, like the online documentation or PDF manual. We always asked this over the past 2 or 3 years. We've already asked this a few times because we want to see how the mood in the community changes. So a few years ago, people were split, maybe 50-50 between a PDF manual and an online documentation. And we would like to know how that changes in order to update our own recommendations and practices. And if you're done with that already, you still need some time, don't worry. If you're done with that already, feel free to take a look at this already, because the next topic will be testing in a minute or so. I don't know how you feel, but when I saw that cartoon, I thought it's surprisingly accurate. Recently, I thought maybe this would have to be changed, especially after the aircraft failures of the Boeing airplanes in recent years. But then I remembered that the aircraft failure of the crashes of the Boeing 737s that happened a few years ago essentially were a software problem, because it depended on only a single sensor. The software was dependent on a single sensor and didn't consider what would happen if the sensor failed. So in a sense, the cartoon is still accurate. What has all of this to do with testing? Testing is a way to prevent software bugs, and testing is intended to make sure that your software does what you think it does. Both CIG and JOS require some form of testing to include your software. Practices could include tests that verify that your code runs properly, maybe results of accuracy or performance benchmarks, pass-fail tests that tell you, yes, it passed, or no, it didn't pass, using something that's called continuous integration to automate your tests, and more detailed testing like unit testing and the method of manufactured solutions. We're going to talk about what that means in a second. JOS also requires tests. If you want to publish a software paper in JOS, you need to have automated tests, or at least manual steps described that guarantee that the functionality of the software can be verified. The main reason, like I said, for testing is that it prevents bugs. You probably know what a bug is. It's a fault in a computer program that causes it to produce incorrect or unexpected results or behave in unintended ways. They were known for a long time. Interestingly, if you ever want to go back in the history of computer programming, Ada Lovelace, one of the first software designers, if you can call it that at the time, wrote in 1842, an analyzing process must equally have been performed in order to furnish the analytical engine, the computer she was working with or programming for, with the necessary operative data, and that herein may also lie a possible source of error. Granted that the actual mechanism is unerring in its processes, the cards may give it wrong orders. That was one of the first definitions of a software bug. You give wrong orders to a computer, it computes the correct reply, but because the orders were wrong, you get the wrong result. There's also this famous story about an actual bug being found in the Harvard Mark II computer by Grace Hopper in 1947. She dutifully taped down the bug in the lab notebook and wrote first actual case of bug being found. But the term bug was used beforehand, but this is a nice reminder that sometimes actual bugs can be in your computer. Not so much today when we're using micro chips, but at the time they were using electronic relays and and tubes where bugs actually could enter the computer. Just to illustrate the importance of this topic, most security risks or attacks or failures that you read about in the news are just caused by bugs somewhere in the program. And they create a huge economic cost and create a risk. There's a litany of important famous bugs that have caused either harm to humans or caused to lose a lot of money. In particular, in space science, several rockets have been lost because of, for example, a missing hyphen in a programming in a program. Not to mention, lately, the largest cyber attacks that have happened so far in 2017, the WannaCry and NotPetya cyber attacks were enabled by software bugs that allowed them to spread quickly and destroy billions of dollars of value in companies. Interesting stuff. Interesting story there if you want to read up on them. But too much for this workshop. So tests are there to reduce these problems and these risks. And what is a test? A test is the process of feeding a program with some input data that you have selected, and then check the output of the program against an expected result. So, for example, if you have a function that should compute the average of an array, the array contains 1, 2, and 3, you would expect it to compute the average as 2. You could call a script that is there to convert one file in one format into another format with a given input file, and you have already created a new output file that you know that's the expected output, and then you compare the output of the program against the existing file. What's not a test is to run your program with some input data. You have some idea about what the output should look like, and based on the output, you guess if the output looks more or less correct. Even though that's something that is often considered a test in many scientific disciplines, it's not technically a test because you do not quantify if your output is correct. Now, as a question, let's consider the following example. A computation produced an output a few months ago. The output was stored, and every time the program is changed, the program is rerun with the same input, and the new output is compared against the original. Would you consider that a test? I need someone brave to step up.
Well, it depends if the result was validated previously and considered truthful. Then yes, otherwise maybe.
Yeah, so certainly if we know that the output is truthful, then it's definitely a test. Maybe I would go further. I would say it is a test. It's a special category of tests that we're going to talk about in a second. Let's first consider what are these different types of tests? What are tests good for? You can, one of the common classification of testing of testing a software is the distinction between verification and validation. Verification means you prove that you do what you intended to do. And that's what we're going to talk about today. Validation means proof that what you intended to do is the correct thing to do. And this is actually hard. To illustrate that distinction, let's take a geoscientific example. A program that does not detect landslides based on satellite data because you coded it the wrong way fails in verification. But a program that does not detect these landslides based on satellite data because it's principally impossible to detect landslides based on this data fails in validation. You might have written a perfect program, but if the physical process doesn't allow this program to work, then the program fails in validation. This step is hard. It depends on the discipline and on the application. That's why we're going to skip it today. What types of verification tests could you write? If you look up different types of tests for software design, there are actually many different types. People come up with different names. We are going to talk about 4 distinct ones right now: manual testing, integration testing, and regression testing, unit tests, and benchmarks. Let's start with manual testing. This is what many scientists think of when they are asked to test their code. You may run your script. You may look at the output of the script. You may think, does this look reasonable? Is there something unexpected? Maybe you run it with a few different combinations of parameters. And if it looks reasonable, you might consider, okay, this is good enough. The problems with this approach is that each run takes you valuable time. You have to rerun the program again. You have to reevaluate yourself again. Does this look correct? And humans are incredibly bad at spotting small errors. There are several psychological problems involved, but one is the confirmation bias. You're looking for reasons to accept this program. You would like it to succeed. And so you're good at just neglecting or rejecting evidence that it's not working. So manual testing should only be acceptable if you're throwing together a one-off figure that's not too complicated. Maybe you're plotting a data set, you don't modify it, and you know exactly that the data set is reliable. That's fine. But if you intend to distribute your program to other users, or you're planning to use the result of a complex calculation in a publication, this should not be an acceptable way of testing your code. Integration tests go maybe 2 steps further than this. First, they automate this manual testing procedure by defining exact input and defining exact output that you expect. And then you make sure that the program creates the exact expected output from the expected input every time you run the test. So for example, you could store a small data set inside of your repository. You could run the software on it and store the output and compare the output that the program gives against a stored output reference result. You could write a function that runs this again and again every time you commit something. These tests can not only save you time, they also catch things that you break later. So it's not just important that the test works when you introduce it. By keeping it around and rerunning it every time you change it, you make sure that you do not break things after they already worked. These step backs are called regressions. And the test that we discussed earlier, where you do not know if the initial result was correct, but at least you know that nothing changed, these tests are called regression tests. So even if you do not know if the initial result was correct, the test is helpful to you because it will tell you if you accidentally change something later. And this happens more often than you think. Some tips for integration tests. You want to cover all important of your application cases. You do not want to have some significant feature in your code that you do not test. You want to make sure that you use small versions of your data set so that the model runs fast. Many of our models might need HPC resources, or a lot of compute time to complete. You want to run your tests fast, ideally less than a minute long. And for that, you need to just shrink your data sets. You do not need to run the full computation at the full resolution for a test. Most of what you're looking for here is whether you change results, not whether the result is 100% accurate. Ideally, you want to test something different with every test. It's no use to have 2 tests that test exactly the same thing on maybe 2 slightly different time series, unless you have a reason to believe that there will be a difference between them. This concept is called orthogonal testing. Each test should be orthogonal to all of the other tests in some way. Sometimes your scripts or programs generate images, and it's always hard to compare images against each other or generally binary output of your program. So you can make these things easier if you write the data itself, ideally also in a text format that can be compared. Another form of tests are unit tests. Compared to integration tests, they are smaller. They do not test the whole program that you wrote. Instead, they run the smallest unit of your program possible. Oftentimes, this is one function at a time. They are much easier to create because you only need to know about the specific inputs to that function, and you can compare the exact output of that function against some reference result. Let's explore a bit what that means. So think back to the example that I said earlier. Say we have a function that computes the running average of some sort of time series. So we have a time series, we get more and more data points, and we want to compute a running average of that series. What are some typical input examples that we should test in a unit test? Again, interactive question for everyone. Extreme cases, someone wrote. Yes, extreme cases are great. What would be in extreme cases in a time series? All the same number. That's a good point. So if you have a time series that has constant values, you would expect that constant value to be the result of your function. What happens if you start a time series? What would be the input for your function? Let's say you just started your seismometer, you received the very first data points. What could happen to your function? Spikes. Divided by 0 or small numbers, exactly. So say when you start this process for the first time, for example, you could get a time series that's empty. What happens then to your function? Does your program crash? Does it give some value that you don't know about? You could have a time series with just one value. You could have a time series where some values are broken. Maybe your whatever measures the time series exceeded its range of values that it could record. So here are some examples or ideas for what input series you would want to test. A time series of constant values, a time series of linearly increasing values. This is nice because you already can easily compute the running average, and you actually have a quantitative comparison. A time series with no values if you just started your measurement. A time series with corrupted values if maybe your instrument has a failure or you exceed the range of acceptable values. And a time series that's shorter than the averaging window to prevent this divide by 0 or divide by some weird number problem. This is easy, or this is best covered by unit tests because they are so easy to write. You can write dozens of them in a very short amount of time. They run extremely fast. You can cover a lot of your code with unit tests. Some advice for unit tests, you want to give them expressive names. You do not want to implement this yourself. There are existing frameworks that you can use. If you're writing in Python, there's PyTest and unit test. If you're writing in R, there's test that. In C++, there are CMake has an integrated C test functionality. But if you're writing unit tests, you likely want to look into Google Test or Catch. Fortran has a list of different testing frameworks that are linked here. There's not one That's the most common one. One thing to keep in mind about unit tests is that you want to avoid having them depend on each other. So try to keep them separate as much as possible. Okay, benchmarks, the next category of tests. Benchmarks are applications of your whole program to a relevant application. So remember when I said integration tests also run your whole program, but you can actually tweak the tests quite a bit they don't have to be realistic. You just need to know what they will produce. For benchmarks, you want to have some sort of relevant application. And they are there to measure the accuracy and maybe the performance of your algorithm. They are pretty expensive to create, and it's pretty hard to produce a relevant benchmark. So they are slightly beyond the scope of this workshop, but I wanted to at least give you 2 examples for different types of benchmarks. One that's commonly created is called a code comparison or a community benchmark, where you can run different programs with the same on the same application case, and then compare the output of the different algorithms. This way you can judge their relative accuracy and performance. Another method that is extremely powerful is the method of manufactured solutions. If your software solves a problem that is based on, say, solving a set of equations, then even if these equations are not solvable in a general case, you can often solve them by creating a very specific case. You can make up a solution for your problem. Let me first illustrate community benchmarks. So this is a community benchmark that was done in the mantle convection community in 2021, where different codes computed the surface topography caused by a thermal anomaly in the mantle below some sort of lithosphere or crust. And then you plot the topography over time for different codes, and you can compare how well these codes do. There are plenty of other examples of well-made community benchmarks available. I put some links into the slides. Here's an example for a manufactured solution. This is from one of my papers earlier, although the solution for this problem actually was known beforehand already. But here we set up a simple convection problem, and by just assuming a solution for a complex flow problem, we can completely define this problem. So in other words, these combinations of independent variables and material parameters are a solution to the equations that we have found by just simplifying the equations. And if we then put in these material parameters into the equations, we would expect to get this solution. And because we know the analytical solution, we can compute the difference between the numerical result and the analytical result based on the resolution of the problem, and can even plot how well the difference between numerical and analytical solution decreases with decreasing resolution or increasing resolution, however you want to look at it. And can compare how this compares to the theoretical expectation for our analytical method. So this is extremely powerful if you can create an analytical solution to the equations that you're solving. Just as a summary about testing, how should you test? Early, often, automatically, to save yourself the time. And the speed of your tests should ideally you want to have a lot of small, fast unit tests, and then as many as possible, of course, but probably less integration tests and even less benchmark cases. But the important part is that you utilize all of these tests in some sort of way because they test different things. being able to catch these bugs is just cheaper than if you would run your program for a while and later on notice that you have a bug in there. One thing that I wanted to mention here is everything I've discussed so far is a traditional approach to testing, in that you write your program first and then you write the test. Over the past 2 decades, in commercial software development, a different approach has been introduced and is now practiced in many companies. This approach is called test-driven development, or TDD. The idea here is that you can write the test first before you have even implemented your software. And then you write the code that satisfies the test. Let's take a look again at our example of the averaging function, how that would look like. Before you have even written your function, you can start with writing a test that says, if I give an input of 0, I would expect my function to return 0, because that's the average of this array. Then you would check that your test actually fails. You haven't written the function yet, so the test should fail, but you should check that. Then you write the function, and you can even write the function in a way that it just always returns 0 for now. Make sure that the test succeeds afterwards. Then you can write a second test. This time use 1 as input and expect 1 as output. The test will fail because your function implementation is not good enough. So you modify the function, then you check that both tests succeed. Then you go on, write a new test that fails again, and so on and so on. This seems a bit weird to write it this way, but test-driven development has been shown to produce better code in less time in many commercial applications, because you think more deeply about what you expect your program to do, as if you would just start coding your program. You automatically create tests for all of the functionality in your program, so you do not forget to test certain things and then have to hunt for bugs later. And you structure your program differently. You structure it in a way that makes it easier to test, which makes it also easier to understand for you later. If you want to follow this approach, there are 3 general rules that are often mentioned for test-driven development. You are not allowed to write any production code until you have written a failing test for it. You are not allowed to write more of a unit test than is sufficient to fail. So in other words, you shouldn't write a unit test that already tests a very complicated behavior before you have even written a first unit test that just checks if the function exists or if you can call it. And you are not allowed to write more inside of your production code, so inside of the function that computes the average, for example, than is sufficient to pass the tests that you currently have. When you've done that, you first have to write a new test. So to just summarize the whole testing part, test early, test often, test automatically to save yourself the time. Tests are very important to prove that your program actually does what you think it does, because most often, if you don't have tests, it doesn't. And it doesn't matter much whether you embrace test-driven development or the classical strategy of write code first and then test later. But make sure that your tests are in place and can tell you that your program is not like maybe correct or looks correct, but that you have defined test cases for which it is correct. If something looks funny or unexpected when you run your tests, it's most likely a bug. Don't try to explain it away. Usually it doesn't work. Usually you have a small bug that in this test case actually produces unexpected results. I wanted to show you, let's see, is this the last? This is the last slide immediately about testing. I just wanted to show you an example of a full test suite. Again, going back to the Aspect software. So the code has more than 10 years of development time behind it. So it has plenty of tests, but the idea behind these tests is a directory called tests. Each test has one input configuration file and one corresponding folder that contains the expected output, in this case, this one. And this folder can contain different files depending on which output you want to test. So screen output here, for example, just contains some output that you would see on the screen. And every time someone suggests changes to the code, all of these tests are run, and the new output of the program is compared against the one that's stored here. Any questions about testing so far?
Yvonne had a few questions in chat. I think you might address those in the talk about when you talk about CI.
Yes. Maybe what is the advantage of running these tests in real time? If the function does not change or changes rarely, testing once is enough. You would think so, but the interesting point is that many functions depend on other functions without you realizing that they depend on them. So I agree completely with you on unit tests of, say, our example of computing an average of a time series. But can I ask, you probably mean, why should I run a test for one part of the program again if only a different part of the program changed over time?
Yeah, I think that's the spirit of my question.
And
yeah,
I think part of that is what I just said, that oftentimes parts of your code depend on other parts without you realizing that they do, especially in larger projects.
Yeah, I mean, your presentation kind of made it clear the merits of doing this. And when you were presenting this, I was just thinking, I'm doing all these tests, but once I've done them, I typically delete these files, delete everything, because it clutters my code. I would have like 50 test functions for just 10 files in the code, or something like that. So it's disproportionate.
Yeah.
So my practical question now is more how to best organize these tests within your repository, so you can clearly see what is the proper code, self-contained, and what is the test. Because the test will be executable programs that are really different from the main goal. And there's a lot of different functions. Typically, for example, I would have a lot of tests for my Fourier transforms to make sure, it's bulletproof. But once it works, nobody's going to change the Fourier transform. So, but I see the merit in showing others that you have done this test.
Yeah, exactly.
Sociological or psychological, it's, I see the merit of that.
Yeah. Also, there's one point about tests that I haven't mentioned yet, and that is it also increases your own comfort when you want to change something. So say you want to see if you can move the Fourier transform to a GPU instead of the CPU, then you would need your tests again. And you feel way more comfortable changing a code base that is tested every time than one where you will have to manually redo a lot of testing steps. About your question about the additional code, most software moves all of the test relevant code into a directory that's called tests. And that's most easily done if you, so in Aspect's case, we can specify input parameters that define the different application cases. Sometimes we also have to change some source code, and we have a system for that by storing a source code file with the same name as the input parameter file. And this source code file will be compiled into the main program when this test is run. So this way, we even keep the test source code separate from the main source code directory. One of the
PRM is a standard format file, or it's just your own?
This is, in this case, this is our own. It's defined by one of our dependencies, the DL2 library, and we just use its functionality. I want to talk about configuration files in the next chapter. This is not ideal. Ideally, you would use a standardized format, but we are a bit bound by our dependencies. And one question in the chat is, I have the issue of over-testing and taking a legacy code that won't automatically pass core tests because there are too many tests that no longer seem useful. Is there such thing as too much testing? I don't know if anyone would agree with me if I would say that it's possible to do too much testing. If you know that what you does changes functionality, then it's okay to say the output of these tests also has to change. So it's acceptable to update test outputs if you know why these test outputs have changed. Also, if you have a lot of tests that, for example, test exactly the same feature, then it might also be okay to remove some of them. They would violate this orthogonality principle that I've mentioned. But generally, it's a rare problem to have too many tests compared to too few tests.
I may give some a bit of context. It's a package that calls another GitHub for reading files with different data formats. Mm-hmm. But that package, that GitHub does not have a license. So as I'm refactoring it, I cannot use these bizarre files from old formats in seismology, mm-hmm. which are called hundreds of times in the main code testing. Mm-hmm. And so it fails.
Yeah, that's a bit more complicated problem. So one thing that is often recommended if your tests depend on outside data is to create something that's called a mock framework for tests. So the question in your case would be if you can pretend that there is outside data without actually having this outside data there. You see what I mean? Like encapsulate it in a function, and in the test, instead of using the actual data, use some made up data. That way, maybe you can like remove that dependency on the outside code part. That might help. All right. So we just have a few minutes left in this session, and we're a bit behind, but I would like to at least cover the part about continuous integration now, and then we'll move the reproducibility discussion into session 3. We talked a lot about, well, then you just automatically run your tests every time, but you need something that helps you to run your tests automatically every time you change it, or you change your program. And this something is called continuous integration. Continuous integration is came up as development practice over the past few decades, and it essentially just means that as often as possible, you integrate your changes into the main version of your code, and you have a service running that every time you do an integration, you also do an automatic build and an automatic test of this build. Many of these aspects are mostly relevant for large software projects, but for smaller ones, it essentially means what I just said, like small incremental changes, then test the changes, then commit. If you collaborate with someone, then also make sure that you merge your changes not just locally on your computer, but make sure that your GitHub version of the software stays up to date as well. And make sure that if you use GitHub or GitLab or any of the online repositories, you use their features to run these automatic tests. There are tools to do this. On GitHub, it's called actions or workflows. GitLab calls them pipelines. If you use neither GitHub or GitLab, or you want to use, don't want to use their services, there's a software called Jenkins. You can do the same thing. Microsoft has another service that's called Azure Pipelines, which also does the same thing. To not get into the details of all of them, here we will just discuss GitHub Actions. GitHub Actions are workflows that are triggered by GitHub and will be executed in your repository whenever a certain event happens. And it will use GitHub's cloud resources for this, so you don't need to provide a computer for this yourself. Events could, for example, be a fixed timeline every so and so often, or events could be every time someone pushes to your repository on a certain branch, maybe your main branch or even some development branch. Or an event could be every time someone opens a pull request. Workflows could be to compile your software, to run all of your tests, to build your documentation, or to update a web page. To set up a GitHub workflow, you just need to put a correctly formatted file into a directory that's called .github/workflows. As soon as you put it in there, the workflow will be active on GitHub. Needs to have a special format though, and I'll show you an example format. This is a format that I've mentioned briefly before, YAML, yet another markup language. And the files look approximately like this. You give the workflow a name, you give it an event on which it is triggered. So in this case, whenever a pull request is opened or something happens with the pull request, this workflow will be triggered. Some special options that I'll skip for now. You can specify some environment variables that should be set if you need that for your workflow. Then you specify a job that should happen. You give the job a name. You can specify which operating system this job should run on. You can make this Ubuntu latest, Mac OS latest, I think, and Windows latest, for example, whichever you want to test on. And then you give it a number of steps that should be executed. The important part here is this part. If you give it a step and say run, then this is just code that is like code that you would type in your terminal. This is just executed inside of a virtual machine somewhere in the cloud. And while it's executed, GitHub will take note of the state of this. So if some of these commands fail, then the whole actions workflow will fail, and you will see that. So I have linked this workflow in the slides in case you want to take a deeper look. But let's take a look at how this looks like for a pull request. So this is one of the pull requests to the Relay software. As soon as you have at least one workflow in your repository, GitHub will show a number of checks down here. In this case, there are more than one workflow active, but they will appear here as checks, and they will either have a green check mark or a red cross, depending on whether they passed or not. You can look at what exactly happened here by clicking on one of them, and then you see the individual steps of this workflow. Let me see if I can show you how exactly this connects to the file that we looked at before. So this is the job named Linux Jammy Container Build. And one of the steps here is called build relay. And it runs these commands. Configure something, and then it compiles it. If I check the results, this is the workflow called Linux Jammy container build. It has one step called build relay. And here it executes these commands that were specified in the file. And this is the output of these commands. And it passed. So if the compile stage would have failed here, if something had changed the file so that it doesn't compile anymore, this step would have failed and would have told you that it fails. And with this, I would like to go into the break because we're running over time. Yeah, Sylvain mentioned it's called integrations in Bitbucket. I would say we're going into the break now, and we will, if you have any questions about this part, we can talk about that after the break. And we will also cover the reproducibility part after the break, and then talk about the actual software publication. Does that sound reasonable for everyone? Any questions we need to discuss before the break? Great. So we will, yeah, like Lorraine wrote, we will be back at the top of the hour in 25 minutes. See you then.